The following is a presentation by General Motors and McCormick Motors Incorporated of Napanee, Indiana, who is solely responsible for its content. Any reproduction or distribution without express written permission by McCormick Motors is strictly prohibited. We hope you find its content informative, educational, and entertaining.
During 2007 and in subsequent model years, Duramax and all diesel engines built for use on United States highways must comply with updated federal emissions regulations contained in the 2007 Highway Rule. In October 1993, the 1990 Clean Air Act amendments requires that diesel fuel for on-highway vehicles contain no more than 0.05% sulfur by weight. Before this, diesel fuel typically contained 0.2 to 0.4% sulfur by weight. All diesel engines produced starting January 1st of 2007 must comply with the new regulations that require the reduction of nitrogen oxide and hydrocarbons by 50% and particulate matter by more than 90% over the current 2004 emission standards. Further reductions will be required by 2010. The EPA 2007 Highway Rule requires a full 97% reduction in the sulfur content of highway diesel fuel. The current low sulfur fuel, or LSF, contains sulfur in a concentration of up to 500 parts per million. The new ultra-low sulfur diesel, or ULSD, contains a maximum of 15 parts per million. To comply with EPA regulations, the 2007 Duramax LMM engine incorporates internal and external hardware modifications, as well as significant electronic software calibration updates. Exhaust aftertreatment incorporating the diesel particulate filter, also referred to as an exhaust particulate filter. The diesel particulate filter, or DPF system, is the primary means of reducing particulate matter emissions for 2007 vehicles. For the purposes of this video, the DPF system refers to the entire exhaust system. Visually, the DPF exhaust system can be readily distinguished by its two most prominent components, namely the diesel oxidation catalyst and the diesel particulate filter. Diesel oxidation catalysts, or DOCs, as they're commonly known, have been used for many years to reduce harmful emissions from heavy-duty off-road machinery. The DOC has a flow-through honeycomb-style substrate structure that is wash-coated with catalyst material similar to those used in a typical automotive catalytic converter. These materials include the precious metals platinum and palladium, as well as other base metal catalysts. Catalysts chemically react with exhaust gas to convert harmful nitrogen oxide into nitrogen dioxide and to oxidize absorbed hydrocarbons. The chemical reaction also acts as a combustor for the unburned fuel that's characteristic of diesel compression ignition. In the process, the DOC increases the temperature of the gas in the exhaust stream. Overall, the DOC effectively reduces carbon monoxide, hydrocarbons, both gaseous and liquid, odor-causing compounds such as aldehydes and sulfur, and the soluble organic fraction of particulate matter. The heated exhaust gas from the DOC flows into the DPF, which also has a silicon carbide substrate with honeycomb cell-type channels. The channels are wash-coated with catalyst material similar to those in the DOC filter. The difference between the DPF and a typical catalyst filter is that the entrance to every other cell channel is blocked. The channels that have open entrances are blocked at the exit end. So, instead of flowing directly through the channels, the exhaust gas is forced through the porous channel walls and exits through the adjacent open-ended channels. Soot particulates in the gas remain trapped on the DPF channel walls, where over time the buildup of trapped particulate matter will begin to clog the filter. The filter must therefore be purged periodically to remove accumulated soot particles. The process of purging the DPF is described as regeneration. When the temperature of the exhaust gas becomes sufficiently high, it incinerates the soot particles trapped in the filter, leaving only residual ash from the combustion. So, the filter is effectively regenerated. Several engine and exhaust system components play roles in raising the heat in the exhaust gas to achieve optimal DPF regeneration conditions. We'll look at this regeneration process in more detail a little later, after we've identified the DPF exhaust system components. There are two exhaust gas temperature sensors that function in much the same way as engine temperature sensors. EGT1 is positioned between the DOC and the DPF, where it can measure the temperature of the exhaust gas entering the DPF. EGT2 measures the temperature of the exhaust gas stream immediately after it exits the DPF. The engine control module monitors the signals from the EGT sensors as part of its calibrations to control DPF regeneration. Next, we have the DPF differential pressure sensor, or DPS. The location of the DPS varies by vehicle. The differential pressure sensor has two pressure sample lines. One line is attached before and the other is located just after the DPF. By measuring P1 exhaust supply pressure from the DOC and P2 post-DPF pressure, the ECM can determine differential pressure, also referred to as delta pressure, across the DPF. Data from the DPF differential pressure sensor is a critical part of the ECM calibrations for controlling DPF exhaust system operation. There's one other new component on the exhaust system. That's the exhaust air cooler located at the end of the tailpipe. The cooler is simply a length of tubing with a narrower center section that acts as a venturi. The cooler is attached to the tailpipe with a bracket that provides a gap between the two. As hot exhaust rushes past the gap, the venturi effect draws surrounding air into the cooler and reduces the exhaust temperature. The cooler lowers exhaust temperature at the tailpipe from a potential 420 to 430 degrees Celsius, or 788 to 806 degrees Fahrenheit, to approximately 270 degrees Celsius, or 518 degrees Fahrenheit. That's quite a significant reduction.